So today we're going to dive into the wonderful world of Turing machines. So I've really struggled to think what the weird best approach would be. Uh, do I give the motivation and results of Turing's paper, or do I start with what a Turing machine is? I don't really know. So we're going to go with my gut feeling, and we're going to start with the motivation for it. So this paper, one of the things it does is it refutes the idea that there is a solution to the Entscheidungs problem, which, as briefly as I can say, a solution, if there's a solution to that's the German word for the decision problem. It's if you can be given an algorithm, given enough time, will it be solvable? And the general consensus as of the writing of this paper was yes. The publishing of this paper and of Alonzo Church's paper completely destroyed any faith that these people had in that. Um, in fact, the mathematician Hilbert was so taken aback by it that he didn't believe it until very near his death. So it's a very fundamental thing to our discipline, and I'm going to do my best to make that understandable. As far as papers go, this one's very short. It's 36 pages, and most, I don't want to say most, but a big chunk of it are pages like this. So as far as the meat and potatoes of explaining what things are, it's very short. So I expect you to be able to read it, and by that I mean run your eyes through it and have the words make sense. But to be able to understand it, it's not easy. Um, I recommended that book, The Annotated Turing, and I'm going to assign some reading for the weekend. I want everybody to read um, the introduction section. So that's page 230, 231, and 232, I believe. Yeah, all the way through this section here. I'm putting the link. You can find this paper everywhere, but there's a link to it. Well, so someone asked, so they thought with enough time a computer could list all prime numbers. Not even sure that's not computable, but yes, in the sense that I can't remember her name. There was she's usually like listed as the first computer scientist, kind of. Someone was the point of the story I'm trying to get across is that a computer at the that one, a computer at the time of this writing was a person. So Turing actually says here, you can compare a man in the process of computing a real number to a machine, which is only capable of a finite number of conditions. So there wasn't a computer other than a person in the minds of people at the time of this, when the decision problem was posed. But the people, I can't remember. I think it was it's not important. Hilbert and his buddies, he's an absolute genius. He's done so much stuff for the world of mathematics. It's not like he's stupid or anything, but they were all so confident that if you could describe an algorithm, then of course it must be doable. So, with a little taste of the context of what this paper was written in, let's get into that problem ourselves. So we all remember the idea that there are uncountably infinite sets, right? Not only did we go over that, that was a question on the first exam, and it will be a question on the final. To be able to show that if you are to be given a function s that generates an infinite matrix, no matter how well you write your s function, I will always be able to create a sequence that cannot be found in any row of that matrix. We did that by inverting the diagonal of the infinite matrix and creating a sequence that didn't exist. So with that in mind, let's consider the following. So we've got n plus as a set of positive integers. So that's 0 is non-negative and not positive. So we've got 1, 2, 3, 4, 5, 6, 7, all of them, all the positive integers. Let's define something called IBS. We're going to refer to that as the infinite, it's the set of all infinite bit sequences. So it is going to be this, and what this means is it's the set of all functions from n plus to the set 0, 1, or the set of 0, 1. So I'm going to give a quick example of a function that would be in this set. Let me find my annotate tool. All right. So I want to go from, 1, 2, 3, 4, 2, 3, 4, 5, 6, whatever, to some ones or zeros and ones and zeros and so on and so forth. So here's a function, f n equals 0. And so my bit sequence for that function is going to be 0, 0, 0, forever and ever. Can anybody else give me a function that would be in this set? So it's a function from the positive integers to either zeros or ones, sequence of zeros and ones. Map even to 1 and odd to 0. Okay, yeah, that works. Let's see. I should do this. If n to 0, it's integer division. I can do it that way if you like. Return. Actually, I like it better this way. We say 1 if even, else 0. Now, I like to say that, but either one's fine. All right, so this is going to give us what? 1, nope, 0, 1, 0, 1, so on and so forth. What does that symbol mean after this is the assignment symbol. This is something nearly every language you've ever looked at gets wrong. So you're used to seeing so if you've got some int variable x and you say x equals 3, this is horrible. That's wrong. It should never be done. Whatever reason, whoever rubbed the genie lamp to make this the convention needs to be cooked in their own pudding, because this is the computer science symbol used for assignment. So let x be assigned to be 3, as opposed to what it should mean, which is this, which is x is equal to 3. Those are backwards in almost every language. So when you do something like if x equals 3, in C, This is going to say if the assignment of 3 into variable x worked, then, which is not what you were expecting. So let's say your variable x is 5 and you type if x equals 3, it's going to be true because it assigned 3 into x, no problem. Um, so when I do this, this is, I'm assigning f of n to be 0 in all cases. Anyway, so there's one. There's another one. So that's what a member of this set looks like. So the reason we have a bunch of these is because I can make a function that will pretty much give me any infinite bit sequence, right? Well, I claim that there is no surjection from the positive integers to the set of all infinite bit sequences. Now, and this is right here an infinite bit sequence. The set of all infinite bit sequences, we've seen this before. This is exactly what I listed out for the proof that the real numbers are uncountable. Let's list all of them and put it in order. So I'm going to say first one, whatever function gives me this. It's the first one. Whatever function. Now, since we don't know what the last one's going to be, I'm going to list it this way. You can list them any way you want, really. There's no perfect ordering to how you want to do this. And I'm going to count in binary in reverse. I'm going to list all those out. Now this should look familiar. I now have a matrix, an infinite matrix of infinite bit sequences. Now, can someone tell me what it means for there to be a surjection from set A to set B? You don't have to be completely precise, just give me the idea. Well stated. There is an injection from B to A, but pretend you didn't know what an injection was. That's right. So this is also known as onto. And Brandon said that injection from B to A, which is 1 to 1. So this says that every element in B has a corresponding element in A. So everything in A gets mapped to something, is what this says. This one says everything in B maps uniquely to something over there. Okay, so if I'm saying that there is no surjection from 1, 2, 3 to our set of all infinite bit sequences, that would mean that there is no way to map the positive integers to everything here. Well, that's the claim. Let's try to give a proof. So let's say I've got some function. I've listed out a couple ones. I'm just going to call this one, let's say f prime. Actually, no, I'm going to stick with f because that's what I have written here. So f is some function from n plus to IBS. Does everybody have an idea of what f would look like? I've given you an example here. I've given you an example here. It takes the positive integers and gives you an infinite bit sequence. So for here, our function is, it doesn't matter what it is. I'm going to take 1, I'm going to plug it in. Well, it turns out it's 0. So that's going to mean 0. All right, I'm going to take 2, I'm going to plug it in. It's going to be 0, so that's the result. So on and so forth forever and ever. If my f is this, then my first value is going to be, let's see, 1. 1 is not evenly divisible by 2, so it's 0. 2 is evenly divisible by 2, so it's 1, so on and so forth. Is anybody unclear on what a possible f could look like? So this f of n, I'm going to make these f prime just so, actually, we'll just make them g. So there's no confusion. It's something. Anybody not have an idea of the form this can take? Any possible function you could think of that maps 1, 2, 3, 4, 5, 6, blah, 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 into an infinite bit sequence. All right. I don't have any objections. So we've got some function f. So for each positive integer, we're going to write the ith sequence for f of I. So that's just instead of n, using I. Okay. So that means that it's kind of what I've been listing out here. So g of 2 would be g sub 2. Note that every instance of this, g sub 2, is part of the functions here. So it's part of our set of all functions. So let's let A be the infinite matrix whose I comma jth entry is f of I comma j for all I comma j and n. We've done this before. This shouldn't be a surprise to anybody. This is the proof we talked about for the uncountable reals. So our matrix looks kind of like this. Doesn't have to be ordered. I just listed them this way. Is anybody lost by that step? Okay. All right. For each I in our positive integers, we're going to say that f sub I is the ith row of A. So because we have 3, which gives us A, we can now say that I'm going to assign I to be the ith row of A. So I've got some function. Let's say this one. I'm going to call this, it's hard to decide if I guess we have to start with 1. So this is the first row. This function here is the first row. The second row is going to be whatever function would give me this, and it's going to look something like 1 if n equals 1, or if we're going with I, 1 if I equals 1, otherwise 0, so on and so forth. Now you can, like I said, you can order these any way you want. Order doesn't matter. All right, so now I've assigned some number to each function that you could possibly ever think of. Now for each I in the positive reals, we're going to define a new function. I'm going to call it D. This is very similar, and in fact, it is, I don't know the right word. This is literally the same thing we did for the reals, just worded a little differently. Now I'm going to define D to be 1 minus f, I can't do subscript, f sub I of I. Now this is going to mean that D is going to be the inverted diagonal of A. So take the first row, and then you take the first digit. It's going to be 1 minus whatever that is. So 1 minus 0 is 1. 1 minus 0 is 1. 1 minus, could be a 1, could be a 0. I don't know. 1 minus 1 is 0. It's going to make some sequence. Now we know that D is not a row of A. Well, I don't need to rewrite it. It's right here. How do we know that? Well, I've just defined D in this way from number 5, and we know from the theorem on inverted diagonals, which is what we use to show that the reals are uncountable, that it's not there. So that means D is not equal to any f sub I for any I. But it's a function from that gives us an infinite bit sequence. So how is this possible? We've listed all the functions from the positive numbers, positive integers, to an infinite bit sequence. That was What? Here? We listed them all. This one's not equal to any of them, but um, it's in there. How is that possible? We have created a function that goes from the positive integers to an infinite bit sequence that's not in the list of all possible functions from um, positive integers to bit sequences. So we have a contradiction here, and the contradiction was the supposition. The supposition was, the supposition was that f is a surjection from, should really write that as surjection, from the positive integers. I don't know why every time I see that, because I want to say the natural numbers, from the positive integers to to IBS. So since we reached a contradiction, the supposition must be false. Therefore, f is not a surjection. Now, when we did this for the real numbers, what did that mean about the real numbers? Or did everybody fall asleep? Did anybody get lost in any of the steps I did here? Someone says not a surjection to the natural numbers. So if you mean that that is what I just showed. Yes, there's no surjection. It's actually the other way around. There's no surjection from the natural numbers, the positive integers, to the set of all infinite bit sequences. Can I re-explain what D is? D, so if you have an infinite matrix, whatever order they're in, so I've got rows of infinite bit sequences. Do you understand what a bit sequence is? Infinite bit sequence? Well, actually, do you understand what a bit sequence is? Okay. Is that a bit sequence? I guess I'll do it over here so recording can see. Is this a bit sequence? Actually, yeah, that's fine. Is that a bit sequence? You would say no. Well, it's a sequence. It's empty. So I've talked about this before. It's called to be vacuously true. This is a sequence of what type? Does anybody know what type this sequence has? Is it a sequence of numbers? Is it a sequence of integers? Is it a sequence of bits? Is it a sequence of potatoes? What is it? What's the type of this sequence? Very good. Its type is anything. It's actually not everything, it's anything. It is simultaneously, I guess you could say this is everything. It is simultaneously every type that could ever exist. So it is also a sequence of bits. Now, is that a sequence of bits? That's pretty obvious. That one, I'm going to go on forever and ever. As long as it's ones and zeros, it's a sequence of bits. So what's an infinite sequence of bits? It's one that just never stops. And everything in there is 1 or 0. So does anybody have a question on what an infinite bit sequence is? Monica asked about the matrix, so I will ask, are you comfortable with what an infinite bit sequence is? Okay, so now envision in your infinite bit sequence, you've got slot 1, slot 2, slot 3, forever and ever and ever. That is corresponding to the positive integers. So I'm saying for every positive integer, 1, 2, 3, 4, 5, 6, 7, forever and ever and ever, that's going to be a spot in your sequence. Define a function that goes from whatever number to that whatever number in your sequence. So your function is going to take 6 to the 6th spot in the sequence, and it's going to be either 1 or 0. Don't know what it is. Depends on how you write the function. Is that clear? Okay. So consider every possible function you could ever write. And I'm going to list out all the infinite bit sequences that could exist. So this one's just zeros. I showed you what that one looks like. It's no matter what your number is, 1, 2, 7, 52, it's going to result in a 0. So your infinite bit sequence is just going to be 0, 0, 0, 0, 0, 0 forever and ever and ever. It's right there. And whatever function you need to make the first one 1 and the rest zeros, it's going to go there. Whatever function you need that's going to make the fifth bit to be 1 and everything else 0, it's going to be in here somewhere. Every possible bit sequence is in this infinite matrix of infinite sequences. That's what D is. It is the infinite matrix of infinite sequences of bits. Every possible sequence of bits you could ever have. Does that make sense? So if you can think of a infinite bit sequence, it's in there. We are subtracting by 1. I'm sorry, that's not D, that's A. A is right here. We are subtracting by 1 to say, now wait a minute, you said all of them are in here, but here's one that's not. So I say every single bit sequence, infinite bit sequence is here. And then the clever person goes, what about this one? Take the first element, first digit from the first row, the second digit from the second row, the third digit from the third row, the fourth digit from the fourth row. And what I'm going to do is I'm going to take 1 and subtract whatever that digit is. And I'm going to make a new sequence out of that. So let's look at the following. This isn't going to be an infinite matrix of infinite sequences. It's going to be a finite matrix of finite sequences. I'm going to give you that one, and that one, and that one. All right, so can you tell me what the sequence that the function D is going to give me for this matrix? Yes, it does. It flips the bits. So let's even make it simpler. Can you give me the first digit that the sequence D is going to give me? First digit of the sequence that D will give me. Wasn't asking you, but thank you. I was asking Monica. Indeed, it is 1. All right, can you give me what the second digit is going to be? Okay, now why is it 0? Because 1 of, that's almost right. It's 1 of F sub 2, 2. So it's second row, second digit. So give me 0. And the third digit's going to be third row, third digit minus 1, or 1 minus that, and it's going to be 0. All right. Is this sequence in that matrix? No, it can't possibly be in the matrix because how we built it. It is different from every row in this matrix but by at least 1 digit. I've constructed a sequence that can't possibly exist in our matrix. So that is what D is. It is a function that gives me a sequence that can't possibly exist in the matrix. So because I said I've got a matrix that has everything, yet somehow there's something that's not there, the supposition must be wrong. The supposition was that there is a surjection from the positive integers to IBS. This is a proof by contradiction. We've done it before, but that was just a quick explanation of it. All right, so back to what I was asking. When we did this for the reals, I asked what did that mean? The answer is that it means that the real numbers are uncountably infinite. The natural numbers are countably infinite. You can always fit them into the infinite hotel. You can't do that with the real numbers. Well, we just did the same proof for something else, and that something else was the set of all infinite bit sequences. So if there's no surjection from a countably infinite set to another set, then it must be uncountable. So we have a theorem here. If A is countable and B is uncountable, then there is no surjection from A to B. Here's a quick proof. Suppose there is some surjection. Since A is countable, there is a surjection from N to A. This may need to read N plus, I don't remember. Now we're going to define a new function. It's going to look like this. H goes from N to B. Let H be some function of composition. Do you guys all know how to compose functions? Does anybody not know what function composition is? That is exactly right. Yep. So if I have two functions, f and g, then f of g of x is apply g to x, and then apply f to the result of g of x. So remember that g is our surjection from N to A. And I'm just going to say, all right, well, whatever that is, I'm going to make a new function, and it's going to apply to whatever that result is. And that new function, so h, which is f of g of x, h takes me from N to set B. All right, since f and g are surjections, h has to be a surjection from N to B. But we can't do that. Why? Because there's no surjection from N to an uncountable set. Can anybody give me a surjection from the natural numbers to the real numbers? If you can, I'll split the prize money with you. So I say that you can't. Can anybody tell me why that we can't? And you don't have to write it all out. Just you could say it in 2 words. Why can't there be a surjection from a countable set to an uncountable set? Uncountable is infinite, yes. So the answer is, well, let's suppose there was. Do all this again. No, I know there's not. This is the second and now third time I've used this argument here. The answer I was looking for is diagonalization argument. I say suppose there is a surjection, meaning everything here gets mapped from something over there. Okay, well, let's make an infinite matrix of all that stuff. And I'm going to define my function d that gives me one that's not there by flipping the bits on the diagonal. Therefore, you're missing one. Therefore, there's no surjection. So everything up to this point was completely logical. That means the supposition must be false. There's a proof that if you've got two sets, one is countable and one is uncountable, then there's no surjection. So, yep. Every proof I'm going through today, you need to be able to write these out. The really important part, because you could just memorize these, the really important part is knowing which steps you're using to validate what you're saying. All right. So any questions before I move on to the next part? Everything we're talking about today is built on the, see, it's literally theorem 3. So 1, 2, 3. Any questions from theorem 1 or theorem 2? And remember, I mean it when I say, please ask me questions, because I'm not looking to blitz through stuff. I'm looking for you to understand things. I feel like my camera is a little high. A hard time understanding infinite. Most people do. How can I help? If I were to define infinite as, well, let's not even go that far yet. I'm not going to use the word cardinality. I'm going to use the word size, but really what this means is cardinality. Your job is to tell me the size of a collection. That's all you're ever going to do. You're going to wake up, got to check into work at 8 o'clock, and you're going to get sheets of paper all day long, and you're going to tell me how many elements are in whatever's written there. So I give you pretty sure I just lost something important, but that's okay. I give you that. What is the size of that? 3. Okay. What about that one? Okay. What if I gave you one and I had 7,000 digits in it? What's the size of that? Okay. What if I gave you a sequence that no matter the amount of time you spent counting it, you would never finish? What would the size of it be? Infinite. That's correct. That's the simplest analogy I can give for infinite. Now, there's a difference between countably infinite and uncountably infinite. If something is countably infinite, step one, how did I lose you? I haven't even said anything yet. I said there's two kinds of infinity. Yes. Countably. Yes, they are both infinite, but one's more infinite, and I'm going to explain why. So do you understand what the natural numbers are? Moreover, do you understand what the positive? Okay, so we got 1, 2, 3, 4, 5, 6, forever and ever and ever. I can count these. These are said to be countably infinite because I can just keep going. 1, 2, 3, 4, 5, 6. This is the infinite hotel. If you can give me a formula to, in one step, go to my room, it is countably infinite. Why do we say countably? Because of the nature of this. 1, 2, 3, 4, 5, 6, 7, blah, 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 blah. Something that is countably infinite has a mapping. Yeah, n plus 1. It has a mapping from this to whatever it is. So if x is countably infinite, there's a surjection from this to that. So meaning that everything here was mapped to by something here. So two sets that are countably infinite have that property. If you don't have that property, then it is uncountably infinite, meaning you can't count it, is the best way I can explain it. So if I gave you infinite sequences all day long for some weird reason, and the reason you know they're infinite is because I put it in front of you and you're like, did you just give me something that goes on forever? And I'm like, yep. And you tell me, okay, it's infinite. And then I say, yeah, but can you count it? The way you would answer that question is, well, let's line up all the possible combinations of it. So if the infinite sequence was random positive numbers in no order, yeah, I believe so, because I believe you can make a bit sequence that just represents that. So I've said before, like, you take a rational number, that's m over n, whatever. I say all possible those. That's your sequence. Now tell me if it's countable or uncountable. Well, the way to show that it's countable is give me a function that goes from this to that. We've done that before. I think that was exercise 1. But now I say, yeah, but it's all of these. In fact, it's not even all of those. It's only the real numbers between 0 and 1. You should say this is uncountable. And I'm like, well, how do you know? And you give me this argument here. I'm going to list them all out, and I'm going to show you that there's one that can't exist. That is the difference between countably infinite, meaning that there's a function that puts you in the infinite hotel, and uncountably infinite, meaning there's no way I can fit that many people. Cannot be done. Because in a nutshell, all right, here's a way to put the people in your uncountably infinite bus in the infinite hotel. And to which I say, yeah, but this guy didn't get a room. How do I know he didn't get a room? Because I used your function to give people a room, and I made this guy. So he exists. Here's his number, and he didn't get a room. That's like 10 minutes on that question, which I'm happy to go over. If you still don't follow infinite and uncountably infinite, probably re-watch some of the earlier lectures. Just make sure IBS can be infinite sequence of anything because of. Oh, I was just saying what was the type of this sequence right there. It has nothing. There's very little to do with IBS. This is just set theory. If I've got a collection of nothing, there's nothing in there for me to tell you what type it is. So it's every type. Yeah. All right. So any more questions on theorem 1, theorem 2? I thought this is going to take me 2 days. It might take me 3. But that's fine. So theorem 2 is a composition of functions. That's a strange way to say it because that's technically not true. I would say theorem 2 uses the idea of function composition to create a contradiction. So in a contradictory proof, in fact, we're not going to be able to get to this. In fact, I'm probably just going to make this homework. In a contradiction, proof by contradiction, I'm going to say assume something. And then I'm going to take that something, I'm going to make some logical inferences. These are all logical inferences. If I'm doing, this is my supposition. This I don't need to justify. I'm just saying something. I'm saying another thing. And now I'm saying something about the stuff I just said. So number 3 is the thing I'm using to justify this. Number 3 says, let A be some infinite matrix whose entries are from here. Okay. For each entry in the positive integers, F is the ith row of A. That I know that because of number 3 and what the integers are. As long as I don't do anything wrong when I go from step to step, and I get to the last step and I come to a contradiction like 0 equals 1, well, I didn't do anything wrong. I didn't make any mistakes. So the only thing that could have happened was that the very first step, the supposition, is wrong. That's how a contradictory proof works. This proof here, theorem 2, says suppose something. Well, blah, blah, and blah. On the way, I'm going to use some function composition. Blah, blah, and blah. Well, I arrived at contradiction. I didn't mess anything up, so the supposition must not be true. Any other questions? All right. Well, let's look at theorem 3 real quick. So we said that we have these functions from the positive integers to an infinite bit sequence. Well, we know that the set of all infinite bit sequences is uncountable. How do we know? That's theorem 1. Well, now, let's just say that there's a function from the positive integers to a infinite bit sequence, but that no matter how hard you try, you won't be able to implement it in Python. Well, that's weird. How's that possible? I'm saying there's a function, but that you can't write it. That's weird. Well, we're going to use the same argument we've been using for everything just like this. So we're going to say, let P be the set of Python function definitions that implement functions from the natural numbers, or the positive naturals, to a bit sequence. Okay. So if you can think of a function that goes from n plus to a bit sequence, there's a Python function definition for it. Okay. And we're going to let's say uppercase P is all of them. Everybody follow? Does anybody not follow? Does anybody not follow step 1? Now is your chance. If you ask me later about step 1, I'm going to probably do nothing. Okay. Step 2. So we've got a set of function definitions, right? Can anybody give me one? Just one? Can anybody give me a function definition that goes from, it takes a positive integer and is going to give me an infinite bit sequence? Yep, that's one. That someone listed 1 if n is equal to 1 and 0 otherwise. Yep, that is a function definition. Well, it's not the actual Python syntax, but close enough. Let's pretend we all know what the Python syntax for that is. So take that syntax, whatever it is, and let's let that represent some mathematical function. And that function is what you just wrote. You actually gave me the mathematical function. You did this part, so good job. Note that this is a function from our function definitions to the set of all infinite bit sequences. Very cool. Now, my next argument is that P is countable. How do I know that? Well, I know that is because it's a set of countable things. Each function is I'm sorry, I meant to say finite things. If I have a set of finite things, is there any way for it to be infinite? So let's say I have a finite set of finite things. Is there any possible way that that set, if I had to write it out, that it would take forever? Literally forever, meaning it's infinite. That's correct. There's no way for a collection, a finite collection of finite things to be infinite. Now, P, I never said that P is a finite collection. So let's say that P can be a infinite collection, but everything inside of P is countable. Moreover, it's finite. Meaning, pick a size, let's call it n. That is the maximum number of characters you can have in a function definition. That means every entry in P has size at most n. So even if I have an infinite number of that, an infinite number of character or function definitions of linked in, can that be uncountable? Well, the answer to that's no. And if if that's not clear, that was an example in the infinite hotel. That is the infinite bus. It's an infinite set of finite things. It's countable because the function definition is a finite string of characters. Now it's 8:50, and you could leave if you want, but you could always do that. I'm going to try to finish through this. Might take me 15, 20 minutes or so, but that's fine. So does anybody have any questions on step 2 or 3? Okay, what's your question?
On number 2, when it says note that I is a function from P to IBS, can you give like an example of that?
Okay, well, sure. Can you tell me what P is?
Isn't P like the set of functions from N?
It's the set of function definitions, yeah.
Yeah.
So take everything that looks like this in Python, take them all, and that's P.
Okay.
And IBS is this. It's the set of all infinite bit sequences. That's this.
Okay.
So think of a bit sequence, put it in the collection. Keep doing that until you have all of them.
So then I encompasses both P and IBS?
I is a function from P to IBS. So what does that
Is there a
mean? It
mapping? Is
means
there a mapping
that,
there or something?
yes, it means that there's some function and it's going to correspond to some entry in IBS. So here's a function right here. Can you see my cursor? I don't know.
Yes, I can see a cursor.
So there's a function. I maps this function to some row here.
Okay.
That's it.
Oh, thanks.
That's all that I is. Any other questions on 2 or 3? Now, to those of you who stayed here, there will be at least one question on this stuff. I'm not going to get into here, but there's going to be at least one question on these theorems on the exam. What it's going to be, I haven't thought of yet. But anyway, any questions on 2 or 3? Okay. So we know that I is a function from a countable set to IBS. P is countable because it's a possibly infinite collection of finite things. So it's no way it could be uncountable. All right. Well, I know that IBS is uncountable. How do I know that? Right here. Actually, technically, it's right here. So we spent the first 30 minutes on. Well, IBS is uncountable. And I is a function from P to IBS. We know that there is no way to have a surjection from a countable set to an uncountable set. Now, why is this statement here valid? Well, it's valid because P is a countable set. How do I know? Statement 3. IBS is an uncountable set. Statement 4. And theorem 2 says that if A is countable and B is uncountable, then there is no surjection from A to B. So, there is no surjection from P to IBS. Anybody not follow? So if I were to ask a random person in the audience, why is IBS uncountable? What would you tell me, other than theorem 1? If I had the question I'm trying to get across is what's the gist of the argument of theorem 1? Can someone tell me? Does it mean that there is an infinite amount of IBS? No, because that could mean that it's countably infinite, and it's not. Diagonalization is how I did it. Can you give me a little more specificity? We can't write a function from n plus to map to all of IBS. Yes. Can that combined with what Zegadam said is what I was looking for. We can't possibly make a function from n plus to IBS, and why we can't to all of IBS, and the reason we can't is because of the diagonalization argument. I'm going to say, all right, give me every function you can possibly think of, and list them all out. List out all the results. Well, you listed them all out, and I'm going to flip the bits on the diagonal, and you're missing one. So you listed all of them. Step 1, you assumed it can be done. Step 2, you listed them all. Step 3, I gave you one that you missed. So we have a contradiction here. So the supposition must be wrong. So IBS is uncountable for that reason. We also know that you can't have a surjection from a countable set to an uncountable set. That's theorem 2. That one's a lot easier. So since we know that I is a function from B to IBS, it can't possibly be a surjection. So since we know that, that means there's an element of IBS. So there is an infinite bit sequence. So 0, 1, 1, 0, whatever. There exists one that does not appear out of our list of function definitions. So we said list all the function definitions in Python, all of them, every single one. Cool. Well, I have a sequence that none of those can make. How do I know? Because I listed out all the sequences they can make and came up with one that's not there. So that means that there's a infinite bit sequence that no Python function can make. That's weird. Python's not a useless little trivial language. It does a lot of stuff. And I'm saying that there is a sequence of bits that it cannot possibly produce. How does that make sense? Anybody have an idea? Like why is that? That's weird. That means that there's something that can't be done in Python. Anybody have an idea why that is? Some problems are just unsolvable. Yeah, that's right. Remember what I was talking about at the beginning of class? What this paper is a response to, and other things, but this paper was a response to the universal agreement that if you can describe an algorithm, then it must be doable. So if you can describe an algorithm to a computer, which at this point in time was a person, if I can describe a process to you, then if I give you enough time, you can do it. Well, Python's a lot faster than you. And I'm describing a process, and I just showed that there's a process that it can't do. That's weird. Some problems are just unsolvable. Pretty much. I would go further to say that some problems are not computable. That's the real lesson of the day, is that there are things that cannot be computed. And here's a very common one. This is the point of the entire class. This class should be named What Cannot Be Computed. If you are asked to by your company or whatever, customers are going to be putting input into your program, and your boss comes to you and asks, "Hey, we're having a lot of problems with inputs causing our program to crash. Can you parse through our input that the customers are going to be giving us and see if it's going to work or not?" And they just say completely in general. If they ask you to do that, what should be your response to them? It's fine if you don't. The response should be, "I can't do that, and here's why." And does anybody know the why? It's fine if you don't. It's what we're going over. This is the thing we're going over now. It's called the halting problem. Um, the halting problem is essentially stated: it cannot be decided whether an arbitrary program, given some input, will terminate. Can't do it. Now, can you do it in specific cases? So to your boss, you say, "Look, I can't do that in general." But if you're saying, like, "Can I check the input for this finite set of things? Will that work?" "Yeah, I can do that." But any possible input, can't do it. And I know every person I went to undergrad and graduate school. It happens. I get an email about it almost every month. They get asked to do that over and over and over. And you will waste time and money um, trying to do something that can't be done. So that's the lesson of the day, kids. Okay. So homework is I want you to read the introduction section on this paper. If you've got the annotated Turing, I would read pages 1 to 30. I'll email this out. The textbook defines some Turing machine stuff. I'm not a huge fan of the way they're doing it. I'll explain why later. We're going to be using, to the best of my ability, we're going to use the definition from the paper. But yeah, that's the homework. Yep. Anybody got any questions? Well, I'm not seeing any questions. So I'm going to stop the recording and let it render.